Good afternoon, anyone. I'm Pierpaolo Modugno from Queen Mary University of London. And as Felipe said, I'm going to talk a little bit about the influence of reaction condition on the hydrothermal conversion of saccharides. So I'm going to give a little bit of an introduction on the topic. So why do we do this? And then I'm going to explain the process of hydrothermal carbonization with the compounds involved in this process. So the organic compounds in the liquid phase and the hydrothermal carbon. And then I'm going to go a little bit deeper into my research activity. So first of all, all of our economy is based on fossil fuels. And from fossil fuels, we obtain both energy and materials in the form of plastics. And so all of these fossil fuels that we consume ultimately ends up in CO2 that we emit in the atmosphere. But this CO2 won't go back to fossil fuels because this process requires millions of years. So we need to shift from this system, from this open cycle to a closed cycle. And for this we can exploit the biomass, the power of the plants to capture CO2 and transform it into lignocellulosic biomass. So from this lignocellulosic biomass, we can derive both fuel and a source of materials, so that all the CO2 that we emit will be again captured by plants to produce more biomass. So this will be finally a closed cycle. So, but the question is, how do we convert biomass, lignocellulosic biomass, into fuels and materials? A good way to do that is the hydrothermal carbonization. Hydrothermal carbonization has been known for a couple of centuries, more or less, and it's a conceptually simple process. It requires an aqueous solution or a dispersion of carbon-containing precursors that gets heated up to temperatures between 180 to 250 degrees. And in this condition, and in self-generated pressure, the carbon substrate first dissolves into soluble intermediates. And these soluble intermediates in the liquid phase are either converted to dissolved products or gaseous products, or polymerized to form a solid product, which is known as hydrochar. And hydrochar can also be formed directly from the solid substrate in hydrothermal condition. So exactly how do we obtain this? How do we obtain fuel and polymers from biomass? If we have a closer look at the biomass, we see that it's made of three main components: cellulose, hemicellulose, and lignin. In hydrothermal condition, these natural polymers are hydrolyzed into their monomers. So cellulose and hemicellulose produces saccharides such as fructose, glucose, and xylose, while lignin is hydrolyzed to phenolic compounds. So in hydrothermal condition, the saccharides can produce organic compounds such as furfural and hydroxymethylfurfural, which we call for short HMF, and lactic acid and levulinic acid. All of these compounds can be converted to form fuel additives, fuel, and polymers. And also phenols can be used as a source of polymers. So we see that everything that we need, basically, so plastics and fuels, can be, in theory, derived from biomass. And if we give a closer look to the reaction of formation of levulinic acid from HMF, we see that it involves the loss of carbon units in form of formic acid. So we see that these three compounds, HMF, formic acid, and levulinic acid, are strictly tied to each other, are strictly related. And then finally, there is the solid product, which is the hydrochar. This hydrochar appears as a brownish black dust. And at the microscope, it appears in the form of carbon spheres, very regular carbon spheres that has the size of roughly hundreds of nanometers to a few micrometers. The chemical structure of these carbon spheres is believed to be composed of furfural units bonded together directly or through aliphatic chains. And the formation of these carbon spheres is believed to consist in the, so it starts from the random polymerization of furfural units to form small soluble oligomers in the aqueous phase. And as these oligomers increases in their molecular weight, they become insoluble, so they start to precipitate. And as they start to precipitate, the nucleation starts. And then, as the reaction proceeds, more and more units of furfural are bonded to the edges of these particles. So the particles increases in size, precipitating and forming this black precipitate that we see at the end of the hydrothermal carbonization. So to understand how the mechanism of formation of this hydrothermal carbon, we need to consider the reactivity of the HMF, of the hydroxymethyl furfural. So hydroxymethyl furfural has two functional groups, the aldehyde group and the methoxy group, and also the ring is quite a reactive group. So a different number of reaction can happen. There can be nucleophilic attack on the aldehyde group, or condensation and esterification on the methoxy group, or addition of one unit of HMF to another unit of HMF via attack on the carbon ring. So regardless of the reaction that happens, all of this reaction can produce soluble oligomers, then starts to precipitate, producing the humins. And as I highlighted before, HMF is strictly connected to formic acid and levulinic acid. So these are the structure of HMF and levulinic acid, and we see, I mean, it's been demonstrated that levulinic acid plays a role in the formation and growth of these carbon particles. And formic acid also plays a role because of its acidity. So as the concentration of formic acid increases in the aqueous medium, the acidity decreases, and so more and more HMF molecules starts to polymerize to form the precipitates. So these hydrothermal carbon, these carbon spheres, are not only a side product in the conversion of lignocellulosic biomass to chemicals. This product can also be used as a advanced material for the production of electrodes for batteries and supercapacitors, or for gas storage and for gas filtration, and also for sensors and drug delivery and heterogeneous catalysts. And all of these uses are derived from the structure of these carbon spheres and its highly functionalized surface. So in my study, my aim is to study the effect of the different carbon source and various reaction times, initial pH, and different acid catalysts. Each of these parameters on the product distribution and yields, and also the chemical product properties and morphology on the hydrochar. So what I did is dissolving glucose, fructose, and hydroxymethyl furfural in water, and so putting these solutions in an autoclave and cooking this solution in autoclave at 200 degrees for various reaction times and in different condition of either neutral condition or acidic condition, and then collecting and characterizing the products. So the first analysis that can be made on the aqueous solution is just measuring the pH. So what I did is collecting the aqueous solution after hydrothermal carbonization of glucose and fructose solution and measuring the pH of this aqueous solution. And what we see from this graph is that as the residence time of this solution in the hydrothermal condition increases, we see that that final pH of the aqueous phase decreases. And this is true for both glucose and fructose solution. And what also we can see is that in any case, the final pH of the glucose solution is higher compared to the fructose solution. And this gives a hint about the different reactivity of glucose and fructose in hydrothermal condition. So what I did is collecting the aqueous solution and analyzing it through HPLC. And so what we see in this graph is the product yields of conversion of glucose in neutral condition in the top graph and in acidic condition in the bottom graph. So what we see is that at lower reaction time, there is a very low conversion of glucose in uncatalyzed condition, and the only product is HMF. But as the reaction time increases, more and more glucose is converted to HMF. So it reaches a maximum at around 4 hours, and then as the and then it declines, and in the meantime, more and more of the product is converted to both hydrochar, and we see that the yield of conversion of hydrochar increases as the reaction time increases, and also levulinic acid. In acidic conditions, HMF is almost undetectable after 3 hours in any of the samples that I made. So for any of the acid that I used. So HMF is not detectable, and the only products detectable are levulinic acid and hydrochar, which are, and the yields of conversion are more or less similar for any of the samples. And this means that the important parameter is the pH, or the initial pH of the solution. And in this condition, and it's not very important which acid gives this pH. So there's not a great difference in conversion for hydrochloric acid, hydrobromic acid, sulfuric acid, and nitric acid. So the same kind of analysis has been made using fructose as carbon precursors. And what we see is that in this condition, in neutral condition, the conversion of fructose to HMF is higher compared to the conversion of glucose to HMF. And it's higher also in shorter time. So after 2 hours of reaction, we see that a conversion of about 15% of fructose to HMF. And as the reaction time increases, the HMF yield decreases in favor of levulinic acid, which remains more or less stable over time, and hydrochar, which increases as the reaction time increases. In acidic conditions, so using starting from a pH of 1.5 and using different acids, we see that the situation is more or less the same of that of glucose. And that means that the addition of an acid to the aqueous medium evens out the differences in reactivity between fructose and glucose. So the next experiment involves the conversion of HMF in different conditions. So HMF alone and HMF in presence of levulinic acid and formic acid. So I prepared 3 solutions of this. 3 solutions, one with just HMF or 0.05 molar, and one with HMF and levulinic acid in the concentration of 0.05 molar, and one with HMF and formic acid in also in the concentration of 0.05 molar. So after an hydrothermal conversion for 2 hours, we see that the HMF consumption in the solution A, where HMF is alone, is about 27%. And the formation of levulinic acid is very low. Is just 2% of the HMF, of the starting HMF is being converted to levulinic acid. When we had levulinic acid in the starting solution, in the solution B, we see that the HMF consumption is lower, and the levulinic acid formation is about 12%, and that means that levulinic acid. So what we see here is that when we add a product in the starting solution, we inhibit the formation of that product in the final solution. While when we added formic acid, so the HMF consumption is still 27%, but the levulinic acid formation is doubled compared to the solution where HMF was alone. And that means that formic acid provides, even if it's a weak acid, it provides enough protons to enhance the conversion of HMF to levulinic acid. And then we proceeded by analyzing the hydrochar through solid state NMR. So what we see is the very well-known NMR spectra of hydrochar, where we can recognize the aliphatic portion, and then 2 peaks that belongs to carbon bonded to an oxygen atom or a double bond to another carbon atom. And so these 2 peaks points out to a structure where there are many carbon-carbon double bonds and also many CO bonds. And then in the high portion of the, in the high ppm, we see the signals that belongs to the carboxylic group and the carbons involved in ketones and aldehydes functional groups. So what we see from this comparison is that hydrochar formed in neutral condition and in acidic conditions are not are apparently from solid state NMR are basically the same structure. And then we proceeded by performing an FTIR analysis of the hydrochar. And the FTIR spectra of hydrochar is very rich of information. So what we can recognize here, so what is shown here is the spectra, FTIR spectra of glucose-derived hydrochar in a neutral condition after different reaction time and in acidic condition after a fixed reaction time 3 hours and in a fixed initial pH of 1.5. So in the first graph, we can recognize the typical peaks of an hydrochar where there are CC double bonds, carbon double bond, the CO double bond, and also there is a very broad band belonging to the OH stretch of the of carboxylic acid or hydroxy group, and also very typical peak, very sharp peak of a CO bond that belongs to a furanic acid, furanic ring, sorry. And also in this hydrocarbon obtained in neutral condition, we can see a peak that belongs to CO double bond in and is very specific of the aldehyde group of the hydroxymethyl furfural. And we can't see this peak in the glucose-derived hydrochar in acidic condition. And that means that in acidic condition, the aldehyde group of the HMF is unstable, so it furtherly converts, so it disappears in the FTIR spectra. And other than this, we can see a relatively higher peak of the of a CC double bond compared to a CO double bond. So that means that when hydrochar is formed in more acidic condition, we have probably a more condensed structure with more CC double bonds, and we also can see this CO aldehyde group of the HMF. So yeah, HMF is unstable in acidic condition. So that was for glucose-derived hydrochar. And more or less the same conclusion can be made for the fructose-derived hydrochar. So we can see again the CC double bond peak, the CO double bond peak of carboxylic group and aldehyde group, and the specific CO double bond peak that belongs to the aldehyde group of HMF. And again, in hydrochar obtained in acidic condition, we see again a higher peak of the CC double bond, a relatively higher peak of CC double bond compared to the CO double bond, and we don't see the HMF aldehyde group peak at all. So that means that what this FTIR spectra suggests is that when hydrochar is formed in acidic condition, the carbon is the carbon is more or less has more or less the same structure, but it is more condensed, so with more conjugation between carbon atoms through double bonds, and with less HMF functional group. And finally, we did SEM microscopy of the hydrocarbon. So what we show here is the SEM micrographs of glucose-derived hydrochar. So what we see is that at lower reaction time, at smaller reaction time, the carbon spheres are smaller in size, and they are around 100 nanometers. But as the reaction time increases, the dimension of the carbon sphere increases accordingly. And also at 6 hours, we see that the carbon sphere starts to fuse into each other to form aggregates of carbon spheres in form of clusters. That's also true for fructose, but we see that we see the formation of bigger carbon spheres at lower reaction time. So just after 2 hours, we see that there is a very recognizable formation of carbon spheres that are bigger compared to those formed from glucose at the same reaction time. And as the reaction time proceeds, we see that the carbon spheres fuse into each other. So these are the micrographs that belongs to the hydrochar formed in acidic condition. And again, we see that in acidic condition, the conversion is faster, as we saw, and this goes well with these results, because we see that the carbon spheres are much bigger in size, and they also starts to fuse into each other in lower reaction time. And that's true for glucose-derived hydrochar and for fructose-derived hydrochar. So we see that the size is more or less the same. And this finally is the hydrochar obtained from HMF after 2 hours. And we see that the structure and the morphology is more or less the same as the glucose-derived hydrochar after a small reaction time. So we see very tiny carbon spheres. But other than that, there is not a big difference. So that means that HMF is definitely involved in the formation of the carbon sphere. So to summarize, we have seen that the reaction time has a positive effect on the size of these carbon spheres. So as the reaction time increases, so does the size of the particles, and also the particle starts to aggregate and to form carbon spheres clusters. And as the synthesis pH lowers, this also has a great impact on the size of the particles, maybe a greater impact. Comparatively, at the same reaction time, in neutral condition we have very small carbon sphere, but in acidic condition we have very big carbon spheres around that reaches a size that is around a few micrometers, around 5 micrometers. So, in conclusion, we have seen that fructose and glucose has a very different reactivity. So glucose is significantly slower in the conversion to HMF, and also harsher condition, so lower pH synthesis or a longer reaction time. So both of these conditions has a positive effect on the conversion of glucose and fructose to products such as levulinic acid and hydrothermal carbon. And each of these conversion happens at the expense of HMF. So HMF HMF declines, and levulinic acid and hydrothermal carbon increases. And also formic acid is, even if it's a weak acid, it's sufficiently strong to catalyze the conversion of HMF to LA, to levulinic acid. And in turn, levulinic acid inhibits the formation of hydrochar from HMF. And also, so regarding the hydrothermal carbon, we have seen that the hydrothermal carbon obtained from acid catalyzed solution has a more condensed structure. We have seen this from NMR spectra and FTIR spectra. And both in low synthesis pH and long reaction time promote the growth of bigger hydrochar particles. And however, low synthesis pH are considerably bigger compared to the hydrochar carbon spheres obtained in uncatalyzed condition. So that's the end of my presentation, and I want to thank you for your